Today's topic, we're going to be looking at Earth cycles. And today's word of the day is interconnected. We're going to see how all of these different cycles interact and are affected by each other. Now, I know most of you are too young to remember Mr. Rogers' neighborhood, but Mr. Rogers always had a word of the day. And for us, today's Mr. Rogers word of the day is going to be interconnected. We're going to see how everything affects everything else. And so let's begin by talking about Earth spheres. Now, you can think of these spheres as major cycles or major systems operating on Earth. And we call them Earth spheres because they all end in the word sphere. Now, the four big ones we're going to talk about are the atmosphere, which is the layer of gases that surround the Earth held in place by Earth's gravitational field, the hydrosphere, which is the circulation of water on Earth, the biosphere, and whenever you see B-I-O, that prefix, what should you be thinking? Life. So all living organisms on Earth are part of the biosphere. And then the lithosphere. We're going to talk more about this today, but the lithosphere is the outer rigid layer of the Earth. Now, we just got done talking about thermodynamics and energy. Remember, everything in nature is open, and so all of these spheres are open systems, and you can see with these arrows, energy and matter is constantly cycled between them. So what happens in the biosphere affects the other three. What happens in the atmosphere affects the other three. What happens in the hydrosphere affects the other three. And what happens in the lithosphere affects the other three. This is, remember, interconnected. Now, before we begin today, what we're going to do is we're going to talk about 8 major cycles operating on Earth. And so at the very end, we'll have 8, but we'll go through each of them individually. And we'll start with our first cycle, biogeochemical cycles. What this is the flow or cycling of matter through both the biotic and abiotic parts of an ecosystem. Remember, we've already talked about that. Now, these can include the transport and transformation of pure chemical substances, our elements. So we have like the carbon, nitrogen, and phosphorus cycles. It can also include the flow of other compounds. So the circulation of water, the rock cycle, even chemicals would all be classified as biogeochemical cycles. So any matter, if it's cycling through an ecosystem, it's a biogeochemical cycle. Now, when we talk about these cycles, we need to talk about something called pools and fluxes. A pool is the part of the ecosystem where the matter resides. Does it reside in the atmosphere, ocean, soil, organisms, what have you? And the flux is the rate at which matter moves from one pool to another. Now, let me give you an example of this. Right now, your body is performing cellular respiration, and it's taking in oxygen from the atmosphere. So the original pool is the atmosphere, where the oxygen originally resides. As soon as you breathe it in, it now moves to the secondary pool, which would be your body. And how fast it moves from the atmosphere to your body is what is known as a flux. Okay? So this cycling, as it moves from one pool to another, the movement, the rate of that movement is called a flux. Our second cycle is the hydrologic cycle. This is the circulation of water on Earth driven by the sun, completely driven by solar radiation. Now, we're going to talk about the 4 main processes. Precipitation, which is the movement of water from the atmosphere down to the Earth's surface in any form. Most people think precipitation is liquid rain. Nope, snow, sleet, hail, whatever. If we're moving water from the atmosphere down to the Earth's surface, we're going to collectively call those processes precipitation. The opposite of this is evaporation. This is the movement of water from the Earth's surface back into the atmosphere. Now, I want to point out something here that's not on the slide, and this is this process called transpiration. Transpiration is the movement of water from the Earth's surface back into the atmosphere if done solely by the action of plants. And so often what you'll see is the word evapotranspiration. That is both of the combined processes of evaporation and transpiration. The third process is runoff. This is the movement of water across the Earth's surface, not in channels. Whenever I think of runoff, I always picture a parking lot during a heavy rainstorm. Have you ever noticed that sheet of water that flows across the parking lot? That's runoff. That's the movement of water in these sheet-like flows as it runs across the Earth's surface, as long as it's not in channels. And finally, we have infiltration. This is the movement of water from the surface into the subsurface. This creates something that we'll talk about later in the semester called groundwater, which is water that resides in the subsurface. Now, let me show you these processes. So let's first start with precipitation, the movement of water from the atmosphere down to the Earth's surface. Here's precipitation, movement of water from the atmosphere down to the Earth's surface. Here's evaporation, the movement of water from the Earth's surface back into the atmosphere. Remember, if it's done by plants, we call it transpiration. Here's runoff, the movement of water across the Earth's surface as long as it's not in these channels. And then infiltration, the movement from the surface into the subsurface, creating this groundwater. Now, we're going to talk about our third cycle, but we're not there yet. So the atmosphere isn't the third cycle. It's something that has to do with the atmosphere. But let's introduce the atmosphere first. It is this invisible layer of gases that surround the Earth and are held in place by Earth's gravitational forces. Now, the two primary components are nitrogen in the form of diatomic nitrogen. Remember, in Earth systems, we talked about covalent bonds. Nitrogen doesn't like to just be N. It wants to covalently bond with another nitrogen to produce something called diatomic nitrogen. That's the N2. That's 78% of the atmosphere. The other main component is diatomic oxygen. Also, an oxygen covalently bonded with another oxygen. That's about 21%. The other 1% are minor constituents of carbon dioxide and then noble gases like helium, argon, and neon. Now, here's the interesting thing. We generally, when we think of the atmosphere, we think of something that's homogeneous, something that's uniform throughout. Well, that's the farthest thing from the truth. The atmosphere actually has a layered or stratified structure with different layers having different properties. So if we start with the lowest layer, this is called the troposphere. This is where weather occurs. So this is the layer closest to the Earth's surface. We then get into the stratosphere. The mesosphere is next. The thermosphere, and the one you don't see here is actually called the exosphere. EXosphere. This is kind of the transition between the atmosphere and outer space. So 5 layers with 5 completely different properties. This yellow line shows you how temperature changes in each layer. So most natural systems are what we call heterogeneous, is they're different throughout. They're not homogeneous. Now, I want to talk about a couple characteristics before we get to our third cycle. And the first one is atmospheric pressure. This is the force that is exerted against the Earth's surface by the weight of the air above. Now, whenever I think of atmospheric pressure, I always like to picture it as a column of air pushing down on the Earth's surface. So at sea level, this is actually where we're going to see the greatest atmospheric pressure. And we actually have a common measurement of atmospheric pressure being the atmosphere. And so at sea level, atmospheric pressure is set to 1 atmosphere, which is equal to 14.7 pounds per square inch. Okay, so that's the standard measurement of atmospheric pressure, is an atmosphere. Now, if, let's say, you're up in the Rocky Mountains, so you're high in the mountains, atmospheric pressure, or the column of air, is going to be much less. And so your atmospheric pressure is going to be less. Okay, so if 1 atmosphere is at sea level, anything above sea level, you're going to have less than 1 atmosphere of atmospheric pressure. We also need to talk about water in the atmosphere. Okay, this kind of ties back to our last cycle with the hydrologic cycle. And we talk about something called humidity. This is the amount of water vapor in the air. Humidity increases as temperature increases. So cold air has very low water content. Warm air has much higher. Now, there's something called absolute humidity. This is a mass of vapor for a given volume of air. Generally, we don't like to deal with absolute humidity. What we want to know is something called relative humidity. This is how close the air is to saturation, with saturation being the maximum amount of water vapor that the air can hold. Once you reach saturation, then the water is going to condense. You're going to form clouds. So relative humidity, how close the air is to saturation. Once again, if we're talking about temperature, cold air has a very low relative humidity. Warm air has a much higher relative humidity. All right, finally, we get to our third cycle, which deals with the movement of the atmosphere, atmospheric circulation. Now, the uneven heating of the Earth causes the horizontal motion of the atmosphere, what we call winds. Now, that uneven heating is driven by 2 processes, insolation and albedo. Let's take a look at those now. Insolation is the amount of sunlight striking the Earth's surface. It's highest at the equator and it's lowest at the poles. So if we look at the Earth here, okay, once again, here's our axis right here. The sunlight coming in our equatorial areas is head on at a 90-degree angle. And so that area is going to receive the maximum amount of sunlight. At the poles, sunlight comes in at an angle much less than 90. Usually it might be between 10 and 20 degrees. So we have a lot less sunlight striking the polar regions. The other process is albedo, and this is the reflectivity of materials, which is tied to an object's color. Lighter materials have a high albedo, dark materials have a low albedo. Now, let's kind of put both of these things together and just think about the materials that we have here at the equator. Okay? We have oceans, blue, we have soil, which is brown or black, and we have vegetation, which is dark green. So at the equator, that sunlight comes down, hits the materials that have a very, very low albedo. So most of that sunlight is going to be absorbed. Low albedo means that the maximum is going to be absorbed. And so if you look at it, highest insolation, lowest albedo combines to create a very hot equatorial area. On the other hand, what's at our polar areas? Snow that has a very high albedo. So most of your sunlight that comes down gets reflected back. So if we once again combine these two, with the minimum amount of sunlight, what minimum amount actually hits the poles is reflected back. And so only a small amount is absorbed into it. And so this creates very, very cold regions. So the poles are cold and the equator is hot because of insolation combined with albedo. And it's this unequal heating which drives the horizontal motion of the atmosphere. Now, we're going to talk about it a little later, not in any great detail, but the atmosphere also has a vertical component. So the horizontal motion are called winds. The vertical motion are what are called circulation cells. We're not going to talk about them. That's beyond the scope of this class, but I at least wanted to mention it. So atmospheric circulation has both a vertical and horizontal component. Our fourth cycle deals with oceanic circulation. And the oceans have two parts that move. We have surface currents and we have deeper currents. Now the surface currents are solely driven by winds blowing over the ocean surface. So as the winds blow across, frictional forces between the winds and the ocean surface is what drives surface currents. And here's a great example of that interconnected nature. It's atmospheric circulation which drives surface oceanic circulation. Once again, everything's interconnected. Now the deeper currents are produced by density and temperature differences. Because of this, we refer to the deeper currents as thermohaline circulation. Thermo for temperature and the haline for salt content, which affects density. Now, essentially, what's happening in the deeper parts of the ocean are we have convective cells. Remember, we've talked about that before. Cold, salty water has a very high density and will sink. Warmer, less salty water will rise. And so in the deeper parts of our ocean, we have these convective cells driven by temperature and density differences. Dense water will sink, less dense water will rise. And so this is thermohaline circulation. Now, here is what our surface currents look like. The red arrows are warmer equatorial currents, and the blue arrows are colder polar currents. Now, in addition to winds, I want to point out one other thing that affects these surface currents: the position of the continents. So as the continental land masses have moved, and we're going to talk about that later on today, these currents have changed as well. Now this is these surface currents. These are the deeper currents. These are these thermohaline circulation. And I want to point out, does this look like this? No. They're driven by completely different processes. This is driven by winds. This is driven by temperature and density differences. So they should look completely different because they're driven by different processes. Now, our first four cycles have all dealt with the Earth. The last four cycles that we're going to talk about deal with the fourth natural science that's important to environmental science. So remember our last topic, we talked about chemistry, physics, and biology. Now we're going to introduce the fourth fundamental natural science of geology. And so our last four cycles all have to deal with geologic processes, so we're going to call them geologic cycles. So our fifth cycle overall and our first geologic cycle is the rock cycle. Now before we talk about the rock cycle, let's talk about the three types of rocks that we see here on Earth. We have igneous rocks. These are rocks that solidify and crystallize from molten rock that we call magma, either deep below the Earth's surface or at the Earth's surface, usually associated with volcanism. So an igneous rock is formed from the cooling and crystallization of magma. Our second type are metamorphic rocks. These are when we take pre-existing rocks, we increase pressure and we increase temperature, and the rocks are physically and chemically altered to produce brand new rocks. I do want to point out one thing. The changes occur in a solid state. So we don't melt the rocks. Once you melt the rocks to produce magma, now you're talking about an igneous rock. So a metamorphic rock is you take a pre-existing rock, usually we bury it, because that will increase both temperature and pressure. The rock changes both chemically and physically to produce a brand new rock. Once again, those changes occur in the solid state. You don't melt it. And lastly, we have our sedimentary rocks. These form either when bits and pieces of geologic materials, what we call sediments, are cemented together, or they can form from biochemical processes. So either processes driven by biological organisms or by chemical processes. Let me give you an example of a chemical process that's very common called precipitation. You probably remember this from your high school chemistry class. You take a saturated solution of something. So let's say that somewhere in the oceans we have a three-dimensional volume of ocean water that's saturated. So it is holding all the dissolved substances that it can. If you add any more material to it, the material that was in an aqueous or dissolved phase will precipitate back out into a solid phase. And so these are called precipitation reactions, and the rocks that we generate from those reactions would be classified as a chemical sedimentary rock. Now let me show you what these look like. So here on the left we have igneous rocks. This is the rock called obsidian or volcanic glass. This cools very quickly at the Earth's surface. This is called granite, very, very common igneous rock. This cools very, very slowly deep below the Earth's surface. They're both igneous rocks, but they look very differently because of essentially the time of cooling. Here's our metamorphic rock. This is a rock called a gneiss, G-N-E-I-S-S. And you can actually see individual layers. You see a layer of white minerals and a layer of dark minerals. White, dark, white, dark. In order to generate that metamorphic rock, you need incredibly high pressures and incredibly high temperatures so that the minerals actually align themselves into alternating layers. This is a sedimentary rock. This is called a sandstone. And you'll notice that it looks like a bunch of sand grains were cemented together. That's how we generate a sandstone. So igneous, metamorphic, and sedimentary rocks. Now let's get back to our cycle, which is the rock cycle. Essentially, this describes how any of the three types of rocks can change over time into any other type of rock. Let's go through this, okay? So let's say that we create an extrusive igneous rock through volcanism. Now, we then subject that rock to weathering processes, and we'll talk more about weathering later on in the semester. But we weather the rock and we break it into bits and pieces called sediments. Those sediments are cemented together to now produce a sedimentary rock. We bury that sedimentary rock, it undergoes metamorphism, pressure and temperature increases. Now you have a metamorphic rock. You take that metamorphic rock, continue to bury it, it melts, generating magma. That magma cools deep below the Earth's surface very slowly to generate a brand new igneous rock, an intrusive igneous rock, that's completely different than what we started with. And so the rock cycle says how we can continually change a type of rock. Now, whenever we're looking at geologic cycles, we have to realize one thing. Most geologic processes operate over hundreds of thousands of years, millions of years, tens of millions of years, or even billions of years. And so if we start with an igneous rock on Sunday, we're not going to get a sedimentary rock by Thursday. Between this and this is millions of years. And so essentially, if you want to look at the rock cycle as essentially the recycling of rocks over Earth's entire history. Our sixth cycle overall and our second geologic cycle deals with something called plate tectonics. Now, what plate tectonics is essentially the outer brittle layer of the Earth is broken into pieces called tectonic plates that have been moving for over 1 billion years. Now, the reason why we think this is about 220 million years ago, we had this supercontinent called Pangaea. Most of you have probably heard about it. So all the continental land masses were clustered together, were stuck together. And now, they're not. We have 7 individual continents that have drifted apart. So from a logical standpoint, what can we say? The plates have moved over time. They were clustered together, now they're not, they moved. Now, in order to understand the mechanics of plate tectonics, we have to look at the layered nature of the Earth. And so the mechanics is that we have rigid lithospheric plates floating on a deformable semi-plastic asthenosphere. I realize you didn't understand any of that. Give me about 15 minutes and you will. But that's the mechanics. That's how they move. Now, the other thing that we're going to talk about is when one of these pieces or plates bumps into another one, we create something called plate boundaries. And we'll talk about the 3 types of plate boundaries that we have. But let's start with the evidence. The picture that you see on the left is what we think Pangaea looked like 220 million years ago. The animation that you see on your right is the breakup of Pangaea. These numbers right here are millions of years before present. So let the animation start over. 200 million years ago, that's what Pangaea looked like. And each of those movements represents a 10 million year interval. And you can see how Pangaea has drifted apart. So once again, if we know Pangaea existed, and by the way, we have really good evidence that Pangaea existed, so nobody doubts that. We now know the continents are in separate positions. They had to have moved. Now, in order to understand the mechanics, we have to get into Earth's internal structure. And first, let's talk about Earth's 3 main layers. And I'm going to start in the innermost layer and work outward. So the innermost layer is called the core. The core is divided into a solid inner core and a liquid outer core. Both layers are composed of dense metals, iron and nickel. The intermediate layer is called the mantle, and then the thin layer on top, the outermost layer, is called the crust. So core, mantle, crust. Now, in order to understand plate tectonics, we need to introduce 2 additional layers. The lithosphere is the outer, rigid, brittle layer of the Earth that includes all of the crust and a small amount of the upper mantle. In this layer, rocks behave like solids, how we expect them to behave. Brittle, rigid solids. Now, right underneath the lithosphere is our second layer called the asthenosphere. Now, The asthenosphere, you're talking about the middle and upper portions of the mantle. Pressure is much higher, temperature is much higher in this layer. And so rocks in the asthenosphere do not behave as solids anymore. They behave as something called a semiplastic. In essence, the rocks in that layer can be deformed. They can be stretched, they can be compressed, they can be bent. This is how I like to think about it. It's not 100% accurate, but remember silly putty in your younger days. Imagine whenever you left the silly putty out of the egg, it kind of got hard, but you could still kind of bend it and stretch it. Think of the rocks in the asthenosphere as kind of hardened silly putty. They can be deformed. That's the important part, ladies and gentlemen. If the rocks in the asthenosphere behaved like rigid, brittle solids, the plates couldn't move. So instead what we have is the outer rigid layer, the lithosphere, floating on top of or gliding over the deformable asthenosphere. And the only way that that can happen is because rocks in the asthenosphere are deformable. That's the key word. They can be bent, they can be stretched, they can be deformed. And so that's the mechanics of plate motion. The brittle lithosphere glides on top of the deformable asthenosphere underneath. Now let me show you what this looks like. And let's first go back to the three main layers. So here's our core, where we have the solid inner core and the liquid outer core, composed of those dense metals. Here's the mantle, the intermediate layer, and the very, very thin layer, outer layer, is the crust. Now to understand plate tectonics, we're going to take a look at this black box. And we're going to introduce our two other layers. Here's the lithosphere, contains all of the crust and a little bit of the upper mantle. Once again, rocks are rigid solids. Here's the asthenosphere underneath, and because as you go into the earth, pressure increases and temperature increases, rocks in here can be deformed. So this layer is gliding on top of this deformable layer. Now, before we leave this picture, I want to point out something as well. There's two types of crustal materials. We have oceanic crust, which underlies our oceans, and we have continental crust, which underlies our continents. There's two main differences between those two types of crust. The first one is probably obvious to you. Continental crust is a lot thicker than oceanic crust. The other one that's not so obvious, but this is how I like to think about it. Do continents stand above oceans, or do oceans stand above continents? The answer is continents stand above oceans. This gets to density. Oceanic crust is much denser than continental crust, and so it sits lower in relation. So the two main differences, oceanic crust is thinner but denser, continental crust is thicker and less dense. That density is going to play a very important role when we get to our plate boundaries. And so here's what the picture looks like. These are Earth's tectonic plates. And we have 7 major plates. These are the large ones. We have the Eurasian plate, the Indian-Australian plate, the Antarctic plate, the Pacific plate, the two Americas, North and South, and the African plate. We also have minor plates. These are the smaller ones like the Caribbean, the Nazca, the Cocos, the Philippine, and the absolutely fun to say Juan de Fuca plate. And so what we're going to talk about next are these red lines. This is what happens when one tectonic plate bumps into another. These are these plate boundaries. And there's 3 main types of plate boundaries: divergent, convergent, and transform. At a divergent plate boundary, one plate is moving in one direction, the other plate is moving in the exact opposite direction. As those two plates spread apart from each other, new magma upwells from the mantle, and we actually create new oceanic crust at a divergent plate boundary. A convergent boundary is when plates collide into each other. And this is where density is a very important factor. And think of it this way. Let's say that we have a continental landmass colliding into another continental landmass. They both have the same density, and so the only place for that material to go is up. And so every single mountain range, from the Andes to the Rockies to the Himalayas to the Alps, have all been a result of a continent converging into another continent. Now we can also have an oceanic plate colliding into a continental plate. In that case, different densities. The denser plate, the oceanic plate, gets pushed underneath the less dense plate. So the denser plate dives back down into the mantle. As it does so, it reaches the depth where that rock melts, creating magma. That magma rises to the surface in the form of volcanoes. Now, as this plate dives back under, we call this a subduction zone. So the denser plate subducts underneath the less dense plate. So in a convergent plate boundary, we'll either generate a mountain range or we'll generate a subduction zone. The last one is a transform plate boundary. This is when plates move horizontally past each other. So one plate will move in one direction, the other plate will move in the exact opposite direction horizontally. Now, just to show you what these look like, I have some animations here. And so let's start with our divergent plate boundary. So once again, this plate is going to move in this direction, this plate is going to move in this direction, and magma is going to upwell from the mantle. Now you'll notice those little bursts of light, those are earthquakes, and then you get the kind of plumes there. That indicates that we have volcanism. So a divergent plate boundary is going to be associated with both earthquake and volcanic activity. We run it one more time. So the two plates spread apart, and we create new crustal material here. Here's a convergent plate boundary. In this case, we have a subduction zone. Now, in this case, we have two oceanic plates colliding into each other, and I know what you're thinking. Well, the two oceanic plates should have the same density, so we should create a mountain range. Well, believe it or not, as oceanic crust ages, it becomes more dense. So there is a density difference here. In this case, this plate is older and more dense because it's the one that's getting subducted down into the mantle. And this plate is going to be younger and more buoyant. As I let this run, the plate dives into the mantle. We melt rock, creating magma that rises to the surface in volcanic activity. We also generate those bursts of light in earthquakes. So a subduction zone will also generate volcanism and earthquake activity. And lastly, our transform plate boundary. One side moves in one direction, the other side moves in the exact opposite direction. We don't have volcanic activity here, but as you can see from the bursts of light, these can produce earthquakes. Think of the San Andreas Fault Zone. Now, I want to kind of take a macroscopic view here for a second. And I said that we are creating crustal material at a divergent plate boundary. We're destroying crustal material at a convergent subduction zone. So as the plate dives back in, it eventually melts, forming magma. You have to look at plate tectonics as a mass balance. Whatever is created at a divergent plate boundary has to be destroyed at a convergent subduction zone because the Earth isn't getting bigger and it's not getting smaller. So think of it as a mass balance. Now, what I want to do is I want to put this picture back up showing Earth's tectonic plates, but now I want to talk about the types of plates. So what you see here in the mid-Atlantic, here's a divergent plate boundary, these blue ones. So the African plate is moving off to the east, the South American plate is moving off to the west. We also have a divergent in the middle of the Pacific, in the middle of the Indian Ocean as well. The red line that you see with the triangles, this is a subduction zone. The triangles point in the direction of subduction. So the Indian-Australian plate is getting pushed underneath the Eurasian plate and also parts of the Pacific plate over here. So these red lines indicate a convergent plate boundary with a subduction zone. Now, I wish they would have used a different color, but over here we have the San Andreas, which is a transform plate boundary. So the Pacific plate is moving off to the northwest, the North American plate is moving off to the southeast. So divergent, convergent, transform. Now I wanted to take a look at our tectonic setting here in the North American, and we have two major ones that influence us, the North American plate and the Pacific plate, and we have three minor ones, the Caribbean plate, the Cocos plate, and the Juan de Fuca. You'll notice that the Juan de Fuca, this thin sliver, is being subducted underneath the North American plate. That then changes to a transform plate boundary in central California down into Mexico. And so on the west coast, we actually have two plate boundaries. We have a convergent in the northern section and a transform in the southern section. And I want you to think about this logically, guys. If we're talking about the U.S., where do we typically see volcanic activity and earthquakes? Is it the East Coast? No, it's the West Coast, because we have a plate boundary that coincides with the coastline. The East Coast, notice, the boundary is way here in the middle of the Atlantic. We have a divergent plate boundary. And so do we see volcanoes in Florida? Nope. Do we generally have a lot of earthquake activities in South or North Carolina? No, we don't. Okay? But we do have volcanic activity here in the north due to this subduction zone, and we have earthquake activity all along the west coast because of the tectonic setting. Now, this entire process is driven by mantle convection. There's that word convection again. So movement in the mantle will determine both the direction and the speed of the plate on top of it. So here's what happens. The core is very, very hot. And so as that heat radiates outward, it actually then moves, because it's less dense, up into the mantle. As it gets to the upper mantle, it cools off, it sinks back down to get heated up again. And so it's this continual movement of heat in the mantle drives both direction and speed of the plate on top of it. So the quicker this convective cell moves, the quicker this tectonic plate will move. The slower this convective cell moves, the slower the plate will move. And so a misconception is people think, well, the plates are moving at the same speeds. That's not the case at all. If we take a look at here, the plates that you see in purple, the North American, the African, and the Eurasian plate, these are the slow movers, 1 to 2.5 centimeters per year. So the convective cells underneath those continental land masses are slower. But if you take a look at the Pacific plate, the Cocos plate, and the Nazca plate, they're all moving much faster, greater than 7 centimeters per year. And when you talk about the trillions of tons of material that are being moved, over 7 centimeters a year is very, very fast. And so we know that that convective cell underneath the Pacific Ocean, man, it's just moving. And it's driving those three plates to move much faster. Our seventh overall cycle and our third geologic cycle deals with earthquakes. And an earthquake is a vibration in the Earth's subsurface caused by the sudden release of energy. the magnitude of the earthquake is related to how much energy is released. So when they talk about the Richter scale is one of several scales meant to measure magnitude. The greater the magnitude, the more energy that was released. And I want to go back to, once again, our Mr. Rogers word of the day, ladies and gentlemen, interconnected. The location of earthquakes is not random. It's linked to plate tectonics. More specifically, we have to generate a fault to generate an earthquake. And a fault is where rocks break and one side moves relative to the other. So if you remember our last discussion, we were talking about forces. If you apply a force to rocks, in some cases the rocks will break, creating a fault where one side moves relative to the other. That's what we need to generate an earthquake. We have to have a fault line. And it's that what happens is the two areas on either side of the fault, one side will get stuck and the pressure will build and build and build until suddenly that side moves sudden. That sudden motion is what releases energy in the form of an earthquake. Now, I want to prove to you that there's a correlation, a link between plate tectonics and earthquakes. And so this bottom picture shows you the plate boundaries again. This top picture, each of those red dots represents an earthquake that had a magnitude of at least 5 that occurred between 1980 and 1990. And notice, if I trace around all these red dots, aren't I tracing around the Pacific plate? I am, ladies and gentlemen. Here's the Philippine plate right here. Here's the top of the Indian-Australian plate here. Here's the top of the Antarctic or bottom of the Pacific plate. Now, are there exceptions? Yeah. Okay. You notice dots that happen in the middle of tectonic plates. So there are exceptions. But I hope you will agree with me when I say this. The majority of earthquakes are linked to plate boundaries because those plate boundaries are areas of instability where rocks are broken and we create these fault lines. Now, let's talk a little bit more about those forces. And let's talk about stress and strain. Let's talk about physics, because I know how much you love it, ladies and gentlemen. A stress is any force that's applied to an object that results in strain. So stress is an applied force. How that object responds to that force is what is known as strain. Now, in the case of rocks, there's two types of strain. We can have brittle strain or brittle deformation, where the rock breaks and we generate a fault. That is what we need to generate an earthquake, is we need brittle deformation or brittle strain. The other type is called ductile or plastic strain, in which the rocks don't break, they're bent, and they create something that geologists call folds. Since the rocks didn't break, we're not generating a fault, and therefore folds or ductile strain does not have the potential to generate an earthquake. Now let's look at this a little more closely, and I want you to ignore these bottom pictures. These are actually just different types of stress that we see. But take a look at up here. So we have a sequence of layered rocks here. And the blue arrows, that's the stress. So that's the applied force. The rocks can then go one of two ways. Here is your ductile deformation or your ductile strain, where the rocks simply bend. Okay? No earthquakes, because you don't break the rocks. In this case, this is brittle deformation. We've broken the rocks. In this case, this side has moved up relative to this side. So here's our fault. It's sudden motion along here that's going to release energy in the form of an earthquake. So brittle deformation can generate earthquakes. Ductile deformation cannot. Now, we need to talk about something called hazards. And I'm going to give you a better definition of this once we get to the environment and human health. We'll talk about hazards in more detail. But for right now, let's just define a hazard as anything that poses a risk to human life or human property, engineered structures. And so there are things that happen in an earthquake that we have to worry about, that are either going to kill us or cause destruction to our engineered structures. The most obvious of this is ground shaking. So that vibration that results from the release of energy shakes the ground. Well, in a lot of cases, if you shake the ground hard enough, things like roads or buildings can fail, and so we can have damage to engineered structures. We can also have ground failure, and this takes one of two forms. So we can have landslides, and this is when we violently shake materials at the top of a steep slope and they move down slope under the influence of gravity. These are what are called landslides or mass wasting events. So in mountainous areas, if we have an earthquake that shakes the material at the top and it slides down slope, this is a landslide. The other type of ground failure is liquefaction. This is when unconsolidated geologic materials have a high water content. And when you shake them violently, what once was a solid now will behave as a liquid. And so what has happened, I kid you not, ladies and gentlemen, is that certain earthquakes have actually caused the ground to flow out from underneath buildings just like it was water. Because when you violently shake those saturated geologic materials, you lose frictional forces, you lose cohesive forces, and the material behaves like a fluid. We can also generate tsunamis. We'll talk about what a tsunami is and how we generate them. Fires, the 1989 Loma Prieta and the 1995 Northridge earthquakes all had major fires associated with them because of broken gas lines. Think about it. All our gas travels in the subsurface, so if we shake it hard enough, we break the gas line. All we need is a spark to have a fire. And then we can also generate floods as well. Think about areas that have dams or levees. We'll talk more about levees when we get to water resources, but a levee is a paired structure built on either side of a river designed to reduce the risk of flooding. Well, if you would have an earthquake in these areas where the dam or the levee would break, these would cause major floods. And so let's talk more about these, and let's start with these structural collapse. This top picture here was a picture taken after an earthquake occurred in Pakistan in the early, I think in the mid-80s. And Pakistan, poor country, the building codes aren't as strict, and you can see you have pretty much complete destruction. This picture was taken after the 1995 Kobe, Japan earthquake. This is one of my favorites because notice the first, second, third, fourth floors, sixth, seventh floors fine. But the fifth floor folded like an accordion. And so that was obviously a structural weakness point that the earthquake took advantage of. All these pictures on the right-hand side are taken after the 2008 Sichuan, China province earthquake, and you can see all the buildings have collapsed. We generally don't build buildings on their side. Here's our ground failure. In January and February of 2001, El Salvador experienced two earthquakes exactly 1 month apart. So on January 13th, they had a magnitude 7.7. Remember, that's how much energy is released. And then a month later, they had a magnitude 6.6 earthquake. This caused massive landslides. So all of this material that's blocking this mountainous road used to be up here. And so it was violently shaken hard enough that the material went down slope under the influence of gravity. Here's another picture. All of this material used to be up here. We shook this so violently that it failed, burying this residential community. And unfortunately, killing dozens of people because these things happen very, very quickly. Here's your liquefaction. This picture was taken after a 1985 earthquake in Mexico City. Mexico City sits on a dry lake bed. And so as you imagine, in the geologic past, it was a lake. And so you might imagine that those sediments have a high water content, and they do. So what happened is the material that this building was sitting on was shaken so violently that the material actually became a liquid for all intents and purposes and flowed out from underneath the building, causing the building to collapse on its side. Here are these tsunamis, which comes from the Japanese word meaning great wave in harbor, and they're often caused by underwater earthquakes along subduction zones. So once again, we have subduction zones. So this is the denser plate being pushed underneath the less dense plate. So picture this, as it gets pushed back into the mantle, it gets hung up, it gets stuck. And the pressure builds and builds and builds until suddenly it slips, releasing energy in the form of an earthquake. That energy then displaces a certain amount of water on top of that subduction zone, creating these tsunami waves that spread out in all directions. Now, in deep water, a tsunami wave may look like an ordinary oceanic wave. Maybe it's a half a foot to a foot tall, but it doesn't look special. The problem comes is as that tsunami wave comes on shore, the bottom of the wave begins to feel the ocean bottom. And so you have friction between the bottom of the wave and the ocean bottom that often causes a 1 foot wave to suddenly become an 8-foot wave or a 15-foot wave, depending on how much energy that tsunami wave has. Now, the other real danger with tsunami waves is they have high velocities. So you might be talking about waves that travel 300, 400, maybe even 500 miles an hour. Once again, in all directions from where that underwater earthquake originated. So it's moving very fast. It has a lot of energy. And as that moves into a coastal area, you might be talking about these waves, these very powerful waves, suddenly rearing up and washing onto the coastline, causing death and destruction. I have a couple YouTube videos of the 2011 Japanese tsunami. I'm not going to play both of them, but I do want to play this one, just to give you some idea of how powerful, how energetic these tsunami waves can be. I want to point out one thing. You see this concrete structure right here? This is called a seawall. This is designed to prevent water from flowing on the other side. It's going to fail miserably here in a couple seconds.
あ、車が堤防を越えました今。船も堤防を越えるかもしれない。
Yeah, that's not supposed to happen. That's like a 30-foot boat. That was a 30-foot boat.